Welcome back. So we're going to continue on talking about Chapter 7 on decimals, and now we're going to talk about operations on decimals. So we're going to start off with addition and subtraction, and the approaches are basically the same, whether you're talking about addition or subtraction. So I'm just going to really talk about addition in detail. Um, and so what we're trying to do here is we're trying to think of how we get an algorithm for talking about addition and subtraction of decimals, and then an algorithm for multiplication of decimals. If we're going to get a decimal, an algorithm for the decimal approach, let's start off with what we know, which is really the fraction approach for decimals. So if I'm going to add these two decimals, let's first start by just turning them into fractions because we know how to add fractions. So let's see, this 3.56 is 356 over 100, and 7.95 is 795 over 100. And here, when I'm adding fractions, I just make sure that I have the same denominator, and then I can just add the numerators. Here I already have the same denominator. If I didn't, I would want to find equivalent forms of the fractions to get the same denominator. But I'll just add the numerators, so I'm going to add 356 plus 795 and put it all over 100. And that is 1,151 over 1,000. And writing this as a decimal, over 100. Sorry about that. Don't know why that 1,000 turned into 100, or 100 turned into 1,000. Now, writing this as a decimal, this should be, 11.51. Okay. All right, so now we want to look at what this does in terms of my decimal approach. So this kind of motivates my reasoning for my decimal approach. We can see that basically what we want to do is we want to be able to get everything over this same denominator and then add the numerators, right? And what that corresponds to is really this idea of lining up the decimals so that we can think of being over the same denominator, and then the digits really correspond to these numerators, right? So if we, in the meantime, kind of ignore the decimal and we just add my digits as we normally would, so adding 6 and 5, I get 11. Adding 5, 9, and 1, I get 16. Oh, sorry, 15. And adding 7, 3, and 1, I get 11. And now my decimals being lined up kind of corresponds to my idea of getting a common denominator. And so I can just bring down the decimal. So that's where that algorithm comes from, is we're thinking of kind of adding those place values. We can further justify why this works using the expanded form. This is not how I would actually add these two numbers, right? I would either use the fraction approach or use the decimal approach, probably just the decimal approach. But the reason why the decimal approach works is we can see using the expanded form of these numbers. So if we write these both in expanded form, if I write 3.56 in expanded form, well, I have 3 ones, I have 5 1/10ths, and I have 6 1/100ths. And for 7.95, I have 7 ones, I have 9 tenths, and I have 5 1/100ths. And now I can see if I just combine like terms, so I have a 3 and a 7, 3 plus 7 ones, right? Combining these two things. And I have 5 plus 9 1/10ths. And I have 6 plus 5 1/100ths. All right? So combining these kind of like terms, I now have this 3 plus 7 becomes 10 ones. 5 plus 9 becomes 14 tenths. Oops, sorry. Parentheses. And 6 plus 5 becomes 11 1/100ths. And then, of course, when I talk about place value, I want to be a little bit careful because if each of these things needs to represent a place value, right? And a place value should not be bigger than 9, right? So here, in order to get this 11 down to the correct place value, I'm going to bring 10 of these guys over here, right? So to do that, what I get is I'll leave everything else the same, and I'm going to bring 10 of them over to the 14, so that becomes 15 1/10. And I'm just left with one of these 1/100ths. So I'm just bringing 10. And I'm bringing really like 10 100ths over, which really is 1/10. Right, so I'm moving 10 100ths or 1/10, so that gives me now 15 tenths. Doing the same thing in my tenths column, right? I want this digit to be, I want this to be a digit, so it has to be less than 10. So I'm going to do the same thing, and I am going to bring this time 10 tenths or 1 over, right? Okay, so this becomes, I'm going to have 11 of these now, and I'll just be left with 5 tenths, and still 1 of the hundredths. And last but not least, let's do this same exact thing with the ones. Well, I guess we don't actually need to do it since we know what 11 ones is. It's 1/10 and 1/1. But we could do the same thing if we wanted to write this out all in expanded form. But since our goal is to really just illuminate why this decimal works, we can write this as just 11 ones, 0.51. But again, of course, we could write this out in expanded form. That would be 1 times 10 plus 1 times 1 plus 5 times 1/10 plus 1 times 100th. And so we see we get the same thing. So this is kind of the justification of where the carrying the 1 that we did in the previous algorithm comes from. It comes from trying to make these numbers in the expanded form into digits, so something less than 9, as opposed to just any whole number that could be greater than 9. Okay, so that's where that carrying the 1 comes from. And the same exact algorithm essentially works for subtraction as well. So we'll go into detail about that. Okay, but multiplication and division are slightly different. So again, we can motivate our, oh, I guess I should mention I have this mathematical task pinned up here. We mentioned this in one of the previous videos in with regards to chapter 6, talking about multiplication. But I think it's good to kind of reiterate this question. So researchers have coined the phrase multiplication makes bigger to describe the student misconception that any multiplication problem, the product is always larger than either of the factors. What is a problem or situation where multiplication makes bigger does not hold? So we mentioned this in chapter 6, but I encourage you to kind of think about this misconception and try to come up with an example of where multiplication makes bigger is false. And similarly with division makes smaller. When would that not be true? And so for examples, I encourage you to look back in the last 2 videos from chapter 6. But I'm happy to talk about this more in detail. Okay, so again, to motivate multiplication, in the decimal approach. We're going to start with just looking at the fraction approach. And so let's take these two decimals and let's turn them into fractions. Okay, so that's 437, or 4,307, or sorry, 43,709 over 100. It's hard to say these large numbers out loud, right? And this is 38 over 10, writing these things as fractions. Now, of course, with multiplication, we don't need to worry about finding a common denominator. We are mostly concerned with that for addition and subtraction. With multiplication, when I have two fractions, I just multiply across. So I multiply my numerators, I multiply by denominators. And when I multiply my numerators, I get this huge number. So 1,660,942, all over 1,000. And now writing this in decimal form, this is 1,660, so 1,660.942. Okay, so we can, of course, always use this approach for multiplying two decimals. But we do, of course, have an algorithm for multiplying two decimals that doesn't involve turning things into fractions. And the motivation for this algorithm comes from kind of what we're doing here. So what we do in this fraction approach is we say basically write these two things as fractions. And when I do that, what I end up doing is I multiply the numerators and I multiply the denominators. So what I end up caring about is the multiplication of these two numerators. That gives me like all my digits, and then the denominator really tells me what place value they correspond to in the end. So when I go now to my decimal approach on the right, what I'm doing is I can start off by completely ignoring what digits I'm talking about. I just want to line up my two numbers. So notice here I don't have any decimal points in this first example, or this first part of the explanation for the decimal algorithm. So I'm just multiplying 43,709 by 38, which is exactly what we do when we're multiplying these two numerators. I again get this 1,660,942. Then to correspond with multiplying my denominators, that's where I want to implement my decimal points. So here in the algorithm, I imagine I multiply like normal, that there's no decimals. And what I do is I look at my decimals here. I look at my decimals and I see that there are 3 decimals to the right. So I add up the two digits to the right and the 1 digit to the right, and I get, well, I should have 3 digits to the right. And what that corresponds to is multiplying these two denominators. So I am multiplying a 10, oops, that. I am multiplying a 10 squared by 10 to the first power, so I should get a 10 cubed here. So that's 3 decimal points to the right. And so again, that's exactly where this algorithm comes from, or motivates this algorithm. And again, thought I wrote this somewhere, but maybe not. Oh yes, I think we can justify this just like we did with in the previous video for section 7.1, we justified in the previous approach when we were talking about addition, we justified the algorithm using the expanded form here. So we can do the same thing. We could write these things out in expanded form and multiply them that way. It would be long and tedious, in fact, even more long and tedious than it was in this example, so I won't go through it, but again, we could motivate this using the expanded form, or justify this using expanded form. Okay, great. So alternatively, we can use this idea of adding the 2 digits to the right plus the 1 digit to the right to get 3 digits to the right when we're multiplying here. When we are multiplying, when we're estimating multiplying decimals. So for instance, in this little example, I have 400 times 3, yeah, this is a similar, or I think I meant to put a slightly different example here. Did I mean to put a slightly different example here? Yeah, regardless, we can kind of use this idea to for estimates as well, to get the rough size of something. Oh, that's right. Sorry, that's what I meant to say with this example was that if I look at 437, the previous example, 437.9 times 3.8, the place value, we should get, it should be about like multiplying, geez, sorry if you're doing that. It should be about like multiplying 400 times 3, right? Because this is approximately equal to 437.09, and this is approximately equal to 3.8. So I should get something around 1200, right? Or at least my place value should be in the thousands, and that's what I get here. So that's actually another way to use this, to do this algorithm, is I can multiply the numbers straight away at the beginning and then use an estimation like 400 times 3 to figure out where the place value should be. Okay. All right. Moving on to division. Again, we can do the same thing where we motivate our algorithm for decimals by looking at what we would do with with fractions. And so let's rewrite this as 154. Oops. Sorry about that. Let me erase. There we go. 15463. This should be over 100 divided by 47 over 10. And now remember my fraction division. I have two ways of thinking about it. I can invert and multiply, or I can get a common denominator, which is kind of, they motivate everything by getting a common denominator. Let's do that here. I think it helps us possibly motivate our algorithm a little bit nicer. So getting a common denominator, our common denominator should be 100. So I'm going to multiply this 47 over 10 by 10 over 10, get a common denominator. So now this is 470 over 100. And my division of fractions tells me once I have the same denominator, which I do, I can just go ahead and divide the numerators, which is where the multiplication by the reciprocal definition of division comes from. And I would just put this in my calculator to estimate roughly what decimal it is, which is maybe cheating, whatever. It's 32.9. We could, of course, have rewritten this as, in powers of 10 in the denominator. But it'd just be time consuming at this point. Okay. Great, so there's our fraction approach, just turning these things into fractions and doing the division. In the decimal approach, so again, there's a similar idea here, which is that I kind of want to start off by ignoring the decimal places and putting them in later. So when I'm dividing two decimals, as I am in this example, 154.63 and 4.7, one thing to notice is that 154.63 divided by 4.7 is the same thing as 1,546.3 divided by 47. And here in pink, I have this justification. Basically, if we rewrite in terms of fractions, each of these numbers in terms of fractions, and we do invert and multiply, we see that we can kind of reduce these two fractions. Let's highlight this piece. We can reduce this this is 10 squared, and this is 10 to the 1. So one of those powers of 10 cancels, and I'm just left with 10 here. So we could rewrite this as 1,546.3 in this first term, and then this multiplying by 1 over 47 is really dividing by 47 in the second term. Okay, so what I'm trying to do here is just write this in terms of, one decimal, right, instead of 2 like I had previously. Then I look at, my second step is really just to ignore the decimals altogether, right, and do this long division. So I do this long division, which is what I have done here. I can do out my long division as normal. I want to line everything up. And now, remember, what I have here is I have a decimal here, and I have no decimal on 47, so I just want to line up my decimals, is my way of using this algorithm. Okay, so again, can be justified if in full detail using the expanded notation, but kind of a nightmare. So we won't do all that, but we can kind of see using the fraction approach where this decimal kind of comes from, the motivation. Okay, so a couple little things to finish off talking section 7.2 here. This is a good time to talk about scientific notation. And we won't spend a lot of time talking about scientific notation, but it's a good thing to be aware of. So scientific notation is basically just a really handy tool for writing very big or very small numbers. And so a scientific notation of a number is in this form A, where A is some digit, so some number between 1 and 10, and it's multiplied by 10 to some power, so 10 to some whole number. And that whole number could be negative, but we'll talk about that when we bring in the integers later on in the course. So right now we're kind of just talking about these guys for very large numbers for where n is positive. Okay, so in scientific notation, I could use scientific notation to simplify each of these numbers. I guess that's 54,500,000,000. And I think that's 346 million that we're multiplying together. So writing 54,500,000,000 in scientific notation. Well, first I want to look at that, those digits, 545, and I want this number to be between 1 and 10. So I'm going to write it as 5.4. And I need to multiply it by 10 to some power, right? I'll just put that 10 to some power. Okay, and so I need to figure out how many powers of 10 do I need to accommodate for all of these zeros that I have. So let's see, that is, so if I start here, I would multiply by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think I get 10 of them. So I would multiply this by 10 to the 10th. And I would do the same thing with 346 million. So I'm going to write this as 346 times 10 to how many powers do I have? Let's see. If I started off with 3.46 to get to 346 million, I'd have to multiply by 1, 2, 3, 4, 5, 6, 7, 8 powers of 10. Okay, so I'm really multiplying these two numbers. Why this is nice is these are all multiplication, right? Is my only operation here. I don't have any addition, so I don't need to worry about distributing or anything like that because, it's one operation, just multiplication. And everything's commutative, right? So since everything's commutative and associative just over multiplication like this, I can go ahead and move my 5.45 and my 3.46 together, and I can move my 10 to the 10th and my 10 to the 8th together. If I multiply this 5.45 times 3.46, I think I get 18.857. And multiplying 10 to the 10th times 10 to the 18th, I notice these two things have the same base. So I can just add their exponents, which is 18. Okay, but notice, be careful, because this is not in scientific notation, and the reason is that this 18.857 is not between 1 and 10. It's not small enough. So that means I need to move this decimal point over 1, right? And in order to do that properly, I'm going to write this as 1.8857, and I'm going to add 1 power of 10. Great. So that's 1.8857 times 10 to the 19th. Okay, so not going to do a ton with scientific notation right now, mostly just using all the properties we've talked about already, like how to manipulate multiplying exponents, commutativity and associativity of multiplication, and decimals and such. So it kind of employs a lot of the stuff that we've already talked about into these nice examples. Okay, so I think the last little thing we want to summarize in this section is talking about repeating decimals. And what we mentioned, where was it? I think it was at the end of section 7.1, is that we talked about, it was this theorem in section 7.1. We talked about when we have a terminating decimal. And we know we have a terminating decimal if and only if the denominator has only factors of 2 or 5 in its prime factorization, okay? And so we're going to kind of circle back to this, and that was at the end of section 7.1, look at decimals that do not terminate. So using long division, we'll often see quotients that will never terminate. And so we have some examples of fractions, like a third, that give me decimals that do not terminate. So notice with a third that the denominator does not only have factors of 2 and 5, right? The factor in the denominator, there's only one factor, right? It's 3, right? So that's what's telling me this should not terminate, this fraction. And so I can see that by actually doing the long division. And if I divide 1 by 3, well, in order to turn this into a decimal, I'm going to rewrite this as 1.0, and divide 1.0 by 3, kind of, right, my algorithm tells me ignore the decimal at first and just line everything up appropriately. So 3 goes into 10 3 times, and I'm left with 9. So when I subtract 9 from 10, I'm left with 1. And I would want to do the same thing again, right? I'm going to add another 0 here. I'm going to bring it down, and 3 goes into 10 3 times. And when I do that, I get 9, right? When I subtract these two things, I get 1. Oh, and I'm really, hopefully, noticing a pattern, right? That's not going to terminate, right? No matter how many times I keep doing this, I keep getting the same result, right? I keep saying, oh, how many times does 3 go into 10? It goes in 3 times with a remainder of 1. Now, of course, to finish off my algorithm, I need to add a decimal point to carry up my decimal point, but this is what this repeating decimal looks like. And so the notation that we use to say that 3 repeats over and over again is we just put a 0.0 with 3 with the bar over the 3. That's what's telling me repeat 3. So similarly with 1/11 here, I could do the same process, and dividing 1 by 11. And since 11 is not factored into just 2s and 5s, right? In fact, 11 is prime. I know that I'm not going to have a terminating decimal. That theorem is what tells me that, right? And I can do this long division, and what I would see is that this is the decimal I get is in fact 0.09 repeating. And so what this notation means is that we have 0.09, and the whole thing 0.9 is what keeps repeating, not just the 9. So when I put the bar over that piece, that's the part that's repeating. We call that repeating piece the period. And so here with 2 over 7, again, 7 is not a factor of just 2 or 5, so I know this decimal is not going to terminate. This looks like 0.285714, and then I would repeat this whole thing 285,714, 285,714 for the rest of my life until I die, and then I'd still keep going, right? So that's what that means in this notation. And again, we could find these decimals by doing this long division if we needed to. Okay, but that connects back to this earlier theorem. Yeah, and I think this next theorem is actually almost literally the same, or basically is actually like literally the same theorem. It says that A over B is a repeating decimal representation that does not terminate. So if we have a fraction and it does not terminate, B has to have some other prime factor, either 2 or 5, other than 2 or 5 in the denominator. Basically, just different form of that theorem. But what this is telling me is if I have fractions, when I turn it into a decimal, there's really just 2 options. If I have a factor of 2 or 5 in the denominator, then I know it's a nice terminating decimal. Or sorry, if I only have factors of 2 or 5 in the denominator. If I have other factors in the denominator, then I'm going to get this repeating decimal. So it gives me really a dichotomy here. So I'll kind of reiterate this at the end here. Actually, I'll reiterate it right now. I think this is, yeah, these are different kind of formulations of the theorem. There's subtle differences here, but I'll kind of summarize what's happening at the end here. Every fraction has a decimal representation, and every repeating decimal has a fraction representation. So basically, to summarize this theorem, what it's saying is denominators with factors of 2 or 5 only correspond to terminating decimals. So if I have a fraction and 2 or 5, only 2 or 5 are in the denominator, I get a terminating decimal. If in the denominator there is at least one factor that's not a 2 or 5, once it's simplified, so in its simplest form, then I have a non-terminating decimal. Okay. So those are really the 2 options. Okay, so just to summarize those 3 theorems, what they're really telling me. Let's circle back to this last little example I wanted to touch on. We want to be able to express, so we did an example of starting here with a fraction and turning it into a repeating decimal. But what if I have a repeating decimal and I want to turn it into a fraction? So let's say I'm going the other way. Here I have this repeating decimal and I want to write it in fraction form. So this is 0.343434 forever and ever, right? Okay, so I want to write this as a fraction. What I'm going to do is I notice that the number of the place where it starts repeating is after the hundredths place here, right? So what I'm going to set this equal to is I'm going to set it equal to 100 times n, and that 100 corresponds to this where my first repetition starts over, which is 3/4 to the hundredths place. Okay, so let's, sorry, never mind. Okay, sorry. Sorry, got ahead of myself. Let's say n is my number here. or sorry, 0.343434. And that's the thing that I want to write in fraction form, right? So now let's look at, this is the hundredths place is my period, right? Where it starts repeating. So now let's multiply this by 100, right? So let's multiply the left-hand side by 100, and let's multiply the right-hand side by 100. So I'll multiply this right-hand side by 100 as well. And so when I multiply this right-hand side by 100, right, what it's telling me to do is to move the decimal place, right? 34. So it now becomes 34.343434, right? And the left-hand side is still just 100n. Oops. And now let's subtract n from both sides. So if I subtract n on the left, remember subtracting, remember n is exactly the same thing as this, just the repeating decimal, right? So I'm subtracting n, which means really I'm subtracting 0.3434, that repeating decimal piece, right? So on the left, right, because that's exactly what n is. So on the left, I'm just left with 99n. And on the right, I'm left with just 34, right? Because I subtracted off all of those repeating decimal places. And now, last but not least, I'm just going to divide both sides by 99 in order to solve for n. So I get that n is equal to 34 over 99. And that's my fraction representation. So I start off and I just say, I want n to be this repeating decimal, 0.34 repeating, and I multiply by the place value of the period. So here the period is in the hundredths place, so I'm going to multiply by 100 on both sides. Then I'm going to subtract off n. And when I do subtract off n on both sides, what it is doing is it is telling me, or it's getting rid of that whole repeating decimal, right? And so I'm just left with a nice relationship between integers. I'm left with 99n is equal to 34, and I just solve for n, and that's my fraction. Okay, so that summarizes these algorithms and decimal representations. A couple of things to look at if you want to do one of these starred problems at the end would be number 39 and 40 in part B of this section would be nice ones that you could do for participation if you would like. All right, we'll continue on next time talking about ratios and proportions and percentages.